Hello everyone, welcome to the course CS22032 Deep Neural Networks. My name is J. Lavanya. I am an assistant professor in Computer Science Engineering Department at Sri Venkateshwara College of Engineering. In this video, we are going to study remaining topics on Unit 1. So here we are going to discuss the concepts of the loss function and the cost function. These functions helps us to measure the error in our predictions and guide the optimization of our models. And we will also study softmax regression, an extension of logistic regression designed for multi-class classification problems. Finally, we will cover model evaluation where we will learn how to access the performance and effectiveness of our models using various evaluation metrics. Loss function. A loss function is also called an error or cost function, which measures how far a model's predictions are from the true values. Its main purpose is to quantify prediction error so the model knows how well or poorly it is performing. During training, the goal is to minimize the loss, which means improving prediction accuracy. Optimization algorithms like a gradient descent use the loss value to update model parameters, weights and biases. Different problems use different loss functions. Regression, mean squared error, mean absolute error, classification, cross entropy loss. Why loss function? So loss functions are essential because they guide the training process of a machine learning model. They provide a clear feedback signals that tells the model how to adjust its weights and biases to improve predictions. They also measure model performance. A lower loss value means the model's predictions are closer to the true values, while a higher loss indicates poor accuracy. Um, Finally, the loss functions shape learning behavior. Different loss functions penalize errors in different ways. For example, some focus more on large errors while others treat all errors equally, directly influencing how the models learns from data. The common types of loss functions. First one is mean squared error and mean absolute error. So let's look at the two common used loss functions in a regression. Mean squared error is defined as it squares the error, which means it penalizes the large error much more heavily than small ones. This makes it very sensitive to outliers but also useful when we want the model to strongly avoid large mistakes. Mean absolute error, it is defined as L equal to 1 by n into summation of yi minus y cap the whole square. So MAE measures the average magnitude of errors without squaring them. So it is more robust to outliers. It treats all errors equally and gives a more balanced view when the dataset contains noisy values. Together, MSE and MAE help us understand the model's error from both the squared and absolute perspectives. For classification problems, loss function measures how well the predicted class probabilities match the true class labels. Cross entropy log loss, which measures the differences between predicted probabilities and the actual class labels. It strongly penalizes confident but wrong predictions and is commonly used in logistic regression and neural networks. Hinge loss, it is mainly used in support vector machines. It focuses on maximizing the margin between classes and penalizes predictions that are on the wrong side of the decision boundary or too close to it. So, Kullback labor divergence loss. So, it measures how one probability distribution diverges from another. So it is often used when comparing predicted probability distributions with the true distributions, especially in probabilistic and generative models. So a loss function is a key part of your model. So it tells us how far off the model's predictions are from the actual true values. In other words, it measures the badness of the prediction. The smaller the loss, the better the model is performing. And when the prediction is perfect, the loss is zero. That's why most loss functions are designed so that lower values mean better accuracy. Next one is loss function. The main purpose of a loss function is to give us a clear mathematical way to measure how well or how poorly a model is performing. This measurement is absolutely essential for two key things. First, parameter learning. The model learns the best value for its parameter by minimizing the loss it experiences on the training data. Optimization techniques like gradient descent or its more efficient version mini-batch stochastic gradient descent help by gradually adjusting the model's parameter in the direction that reduces this loss. Second one is evaluating the model quality. The loss function tells us how far off the predictions are from the actual values. It acts as a reliable measure of how well the model is fitting the data. There is actually a probabilistic reasoning behind using loss functions. In many cases, minimizing a loss function is the same as the performing maximizing likelihood estimation, assuming we make certain assumptions about the noise in the data. For example, if we assume the data has additive Gaussian noise, then minimizing the mean squared error is mathematically equivalent to maximizing the likelihood of the observed data under that assumption. In deep learning, this idea is taken even further. Training deep models means repeatedly updating their parameters to make them better and better at making predictions, and we do that by minimizing a well-chosen loss function. Cost function. Cost function, also called as a loss function or error function, which measures how wrong a model's predictions are compared to the actual value. The main objective of training a machine learning model is to minimize the cost function, because a lower cost means lower error and better model performance. Machine learning models learn by adjusting their parameters such as weights and bias. To find the correct values of these parameters, the model needs a clear feedback about how good or bad its predictions are. The cost function provides this feedback by converting prediction errors into a single numerical value, helping gradient descent determine the direction in which parameters should be updated, ensuring the learning process moves towards minimum error and optimal performance. In linear regression, the common cost function is mean squared error. So it is also denoted as MSE. MSE calculates the average of the squared differences between predicted and actual values. It is well suited for continuous values, producing a smooth convex function that is easy to optimize using gradient descent. Minimizing MSE helps the model to find the best fit line that predicts values as accurately as possible. So MSE is not suitable for classification problems or logistic regressions, because these involve probabilities and discrete classes, not continuous outputs. Using mean squared error in logistic regression creates problems. The resulting functions becomes non-convex, meaning it has a multiple peaks and valleys. This leads to many local minima where gradient descent can get stuck. As a result, learning becomes unstable and slow. Mathematically, combining the sigmoid activation with squared error does not behave well, making optimization inefficient. In logistic regression, the model predicts a probability y cap equal to sigma of W transpose f of x plus b. So our goal is if the actual class y equal to 1, the predicted probability y cap should be close to 1. If the actual class y equal to 0, the predicted probability y cap should be close to 0. To measure how well the predicted probabilities match the true classes, we use log class cross entropy loss. Log loss penalizes predictions that are confident but wrong, ensuring the model learns to produce accurate probability estimates. In logistic regression, we use log loss, also called binary cross entropy. So it is used to measure how well predicted probabilities match actual labels. For a single training example, if y equal to 1, if y cap is close to 1, cost is low. If y cap is close to 0, cost becomes very high. If y equal to 0, if y cap is close to 0, cost is low. If y cap is close to 1, cost is very high. So the combined formula binary cross entropy or log loss, which ensures the model is strongly penalized for confident wrong predictions, guiding logistic regressions to produce accurate probability estimates. Log loss has a key property that makes it ideal for logistic regression. So it is always positive. The logarithm of numbers between 0 and 1 is a negative, and the negative sign in the formula ensures the cost is always positive. Convex function. Log loss is convex, meaning it has only one global minimum. This ensures that gradient descent converges smoothly to the optimal solution. It punishes confident wrong predictions heavily if the model predicts a probability very close to 1 for the wrong class. Example, true label equal to 0, predicted equal to 0.999. The cost becomes very large, forcing the model to correct itself quickly. These properties make log loss stable, reliable and effective for training probabilistic classifiers. Visual intuition of log loss. If y equal to 1, predicted probability equal to 1 tends to cost equal to 0. So perfect prediction. So predicted probability is tends to 0, which means the cost tends to infinity. Wrong prediction. If y equal to 0, predicted probability equal to 0 and the cost equal to 0, which is a perfect prediction. And predicted probability is 1, the cost is infinity, it is a worst prediction. So log loss strongly pushes predictions towards the correct class, especially when the model is very confident but wrong. Gradient descent uses the cost function to update the weights during training. W equal to W minus infinity of dou j by dou W. Here j is the log loss cost function. The derivative is similar to linear regression, but y cap comes from the sigmoid output, not a linear prediction. Gradient descent adjusts weight in the direction that reduces the cost, gradually improving the model's prediction. When a problem has more than two classes, we use softmax activation in the output layer and cross entropy loss to measure prediction error. Softmax converts raw scores into probabilities for each class. Y cap ik equal to e to the power of zk divided by summation of j equal to 1 to k e to the power of zj. Here cross entropy loss for a signal example. Here where k equal to number of classes, y ik of 1 equal to if class k is correct. Y cap of ik equal to predicted probability for class k. So this loss function ensures the model assigns a high probability to the correct class and low probability to incorrect classes, with generalizing the binary logistic regression concept to multiple classes. So next one is cost function. A cost function is a core concept in neural network. It's a mathematical tool that tells us how well the model's predictions match the actual target values. In simple terms, it measures the error, the difference between what the model predicts and what it should have predicted. This measurement is crucial because it guides the model during training. The purpose of the cost function can be broken down into two main points. First one is error measurement and then second one is optimization guidance. In error measurement, it acts as a it helping us to evaluate the performance of the neural network. And second one, optimization guidance. It in during the training period, algorithms like gradient descent use this cost to update the model's weights and biases step by step, so it gets better at making accurate predictions.